Okay, Math 9s, welcome back. In this next video, we'll look at the square roots of non-perfect squares. Last section, we looked at the square roots of perfect squares. Now we're going to look at strategies to deal with non-perfect squares. Okay, so our focus here is to approximate the square roots of decimals and fractions that are non-perfect. And then we'll also take a look at the Pythagorean theorem to solve some problems. Okay, so the big tool that we'll use for finding or approximating is a key word because we're not going to get the exact number because we are going to be doing these questions without a calculator. So we are going to approximate decimal non-perfect squares using benchmarks. So here's what using benchmarks looks like. Benchmarks, I like to think of, okay, well 7.5, is that a perfect square? No. So if we think of the perfect squares below and above 7.5, below 7.5, we have the square root of 4. We know that 4 is a perfect square, and the one above 7.5 is 9. So if I come back over here, the square root of 4 is 2, the square root of 9 is 3. When you're using benchmarks, your top line here, 2 and 3, those should be integers that are consecutive or come one right after the other. So the next thing is to think of, okay, well, where would 7.5 fit on this line? Now, if I'm looking at this bottom line, I'm going to put this square root of 7.5. I don't know, if I had to guess, it'd be somewhere right about there. And what that does, it gives me a visual to see, okay, well, if I had to guess where in between 2 and 3 the square root of 7.5 fits, if I had to guess or approximate, that'd be approximately 2.7. Okay. Next one is root 40. Same thing, we look at that. First, we ask ourselves, hey, is that a perfect square? No, there are no two numbers that will multiply to give us 40. So I'll look at the perfect squares that are below and above 40. Those are 36. Square root of 36 is 6, and the square root of 49 is 7. These two numbers on top are integers, and they are consecutive. If I had to put 40 on this bottom line, probably go somewhere around here. And then to estimate this, I'd say that's maybe, I don't know, 6.3. Okay, and we'll use our calculator to check these later as well, but for now, that's just using benchmarks to approximate. Okay, if you're going to approximate fractional or fractions that are non-perfect squares using benchmarks, with this one, we'll use a bit of an approximation strategy. So square root of 8 over 5, I'm going to look at each the numerator and the denominator. I'm going to choose or find perfect squares that are close to, in this case, 8. So a perfect square is 9. The one on the bottom, one that's close to that would be 4. And if I'm going to find the square root of 9 over 4, that's going to be approximately equal to 3 over 2. Okay, and the approximately equal to sign is a little squiggle like that, or an easier one, or a cleaner one, I guess, to write is an equal sign with a dot on top. Okay, the next one, root 3 over 10, that's approximately equal to, hey, that's like 4 over 9, which is approximately equal to 2 over 3. Okay. Now, if we're going to use our calculator to do that, or to find the exact value of a non-perfect square, or any number, in fact, we can do the square root of 19 over 6. Now, how to do this in your calculator? The easiest way is to put 19 over 6 and hit your equals button. And then when that number is in your calculator, while that number is still in your calculator, then just go hit your square root button and hit equals again. And in this case, you should get a number that's around 1.78. Now, when you do the square root of this number, you're going to have a whole bunch of other digits here in your calculator, and those numbers are not going to repeat. They are not going to terminate. So this is an irrational number. This is irrational number. And the number that we're going to write on our page, it's an approximation. So I'm going to use that dot. I'm going to use that dot on top of the equal sign. Again, that tells us that it's approximately equal to 1.78. Okay, 62.3. Punch that in my calculator. That's about approximately equal to 7.89. Okay. Okay, the backside, for us to find a number with the square root between 10 and 11, well, I'm going to use a a number line again. I love the number line. And we're going to use it in the exact same fashion. So if we're looking for a number with a square root between 10 and 11, if we think of the bottom being the square root, sorry, the top being the square root and the bottom showing the perfect square, we think of 10 squared as 100 and 11 squared as 121. So any number in between here, in between 100 and 121, any number in there is going to give us a square root in between 10 and 11. So to answer this question, I don't know, we can pick one of a bunch of numbers, but we can choose 105, we can choose 111. So you get the idea. If we were asked to find this, we can just say, hey, numbers can be like 105. Okay. Okay, Pythagorean theorem, it's a really useful tool. You've likely seen this before in earlier math classes, and that is just a squared plus b squared equals c squared. So a quick recap of that. C is a really important side. That is called the hypotenuse. When you're setting up your Pythagorean theorem, whatever number is your hypotenuse, it has to go on a side by itself. On the left side, we have two numbers that are added together, but the hypotenuse should be is important that it's on the side by itself. Okay, the two sides that are not the hypotenuse we call legs, and just this diagram over here, this visual is showing, hey, a squared, this is like side A, B, and C. So if you take A and square it, that's going to be, well, in this case there are 9 units, or 3 squared. This B squared is, well, if you have 4, the side length of the square is 4, the area is 16. So the area of this square up here is going to be the sum of these two, or 16 plus 9. So the area of the square attached to the hypotenuse should be 25. And then to find the actual side length of that square, we now know, hey, we could just take the square root of 25, and the side length is going to be 5. Okay, so there's just a visual to show how that looks. Okay, how we apply that to Pythagorean theorem questions, we always are going to start with our Pythagorean theorem formula, and then after that we have to identify, hey, what is going to be the C side? What is going to be C? Our hypotenuse is always the side that's directly across from our right angle. Okay, so this side has to be the one that goes into C, or the side that's by itself. Okay, these other ones, the legs, I'm just going to plug in here. It doesn't really matter which order you put those in. All that matters is that that side is R, or sorry, that C, we put in R for C. Okay, so now if we just do some math here, sorry, that's 2.25. 6.5 squared is going to give us 42.25, and that's going to be equal to R squared. If we add those two numbers together, I'm just going to write these and swap the sides of these two. That'll be 44.5. And I talked earlier about doing the opposite operation. So if you, right now we have this squared number, so the opposite operation to squaring would be to take the square root. Golden rule of algebra says we do the same to both sides. So the square root of a squared number is just going to give us that number itself. Okay, and the square root of 44.5 is approximately equal to 6.67, and we'll include units here, which in the question were given as meters. Okay, next one, again, we'll start in the same spot as with every Pythagorean theorem question. We'll write down the formula. Okay, then we will identify what our hypotenuse is, and that's important because that 21, which is the hypotenuse, has to go on the side by itself. Okay, we'll fill in some numbers for the legs. Okay, then we have to do a little bit of algebra here. So 15 squared is 225. 21 squared is 441. Okay, and then the operation that I'm going to do, the algebra step, is going to be to subtract 225 from both sides. Talked about opposite operations over here between squared and the square root. Well, the opposite operation to this adding is subtracting. So positive 225 minus 225. These two are opposites. They will cancel out. Okay, our next line should look like, hey, x squared is going to be 216. And if we do the square root of that, sorry, I'll write that in here. Our x squared, if we do the square root of that, then our x is going to be approximately equal to 14.7. Okay, there are no units given, so we'll just state it as 14.7. I always like to do a little final check here and just go back and say, hey, 14.7, does that make sense for here? Does that make sense for this side, 14.7? Well, this side, we know that 21 has to be the longest side, so 14.7, it's less than 21, so yeah, that makes sense. It's a number that would fit for that question. Okay, so big idea for this section. Big idea is that we are able to approximate square roots. And we're able to apply the Pythagorean theorem. Okay, and our textbook assignment will be from page 18. We'll do numbers 4 to 12, a few questions from each ACE. Then we'll do 13, 16, 20, and then we'll have a challenge in here. The challenge question is number 23. Okay, so I hope that gives you an idea of square roots of non-perfect squares and the Pythagorean theorem. Thanks for watching, and we'll see you soon.